Review for the quarterly assessment. So the first question here, we want to write the electron configuration for these atoms and ions. So sodium is going to have a total of 11 electrons. So we will always start with hydrogen. So hydrogen would be 1s1, 1s2, write down what we got, 2s2, then we have 2p, 1, 2, 3, 4, 5, 6, 2p6, and then we get down to sodium, which is 3s1. Next, we have calcium. So regular calcium would have 20 electrons total, but this is calcium plus 2. So we're going to take off those last 2 electrons, and it would be the same configuration as argon. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, to get all the way over to argon. Regular calcium would have this 4s2 electrons here as well, but since this calcium has lost 2 electrons, we're going to get rid of those 2 valence electrons. Next up, we have phosphorus. So phosphorus has a total of 15 electrons. So that would be 1s2, 2s2, 2p6, 3s2, and then 3p1, 2, 3. The next one that we have is chlorine. So chlorine normally has 17 electrons, but since we have chlorine minus 1, we have 1 more electron, giving us the same configuration as argon. So that would be 1s2, 2s2, 2p6, 3s2, 3p. So 3p5 would be regular chlorine, but since this is chlorine minus 1, it's going to be 3p6. Now we want to rank these elements from highest to lowest for each of these periodic trends. So first we have electronegativity. So electronegativity is how well an atom attracts electrons that are being shared in a bond. So for example, if you have a bond between hydrogen and fluorine, fluorine is much more electronegative. So those shared electrons are going to be drawn much closer to fluorine than they are to hydrogen. So we're looking at a few elements here. We're looking at these 4. So the highest electronegativity, we have a couple of choices here. So this row has 2 energy levels, and the one underneath it has 3. So 2 energy levels is going to be more attractive than 3 because it allows those valence electrons to get closer to that positive nucleus. So then between oxygen and fluorine, they both have 2 energy levels, but fluorine has 9 protons, whereas oxygen only has 8. So we would predict that fluorine would be the most electronegative, followed by oxygen. So then S and Cl both have 3 energy levels, but Cl has a more positive nucleus, so that's going to be more attractive than sulfur. Now we want to look at ionization energy. So ionization energy is how much energy you need to take an electron away from the atom. So the electrons are negative and they are attracted to the positive nucleus. So you have to put energy in to overcome that attraction if you want to take away one of those electrons. So we're really asking which one of these is it hardest to take an electron away from. So here's our choices. Carbon and nitrogen have 2 energy levels, whereas silicon and phosphorus have 3. So Carbon and nitrogen are going to be harder to remove an electron from because the electrons are closer to the nucleus in the second energy level as opposed to the third. So then between carbon and nitrogen, both have 2 energy levels, but nitrogen has a more positive nucleus, meaning that it will be harder to take an electron away from nitrogen than carbon. Then between phosphorus and silicon, they both have 3 energy levels, but phosphorus is a more positive nucleus, so it would be harder, it would require more ionization energy to remove an electron from phosphorus than silicon. Next up, we want to look at atomic radius here. So we have these 4 choices here. Na and Mg have 3 energy levels. K and Ca both have 4. So we know that K and Ca are going to be bigger than Na and Mg because they have 1 more energy level. But between calcium and potassium, calcium has a plus 20 nucleus, 20 protons. So it's going to have a slightly smaller radius because its nucleus is a little more positive, and that brings the electrons in a little bit closer. So the largest radius would be K, followed by Ca. And then between Na and Mg, Na would be bigger because its nucleus is less positive. So use shielding to explain why the radius of rubidium is larger than the radius of potassium. So for potassium, we have 4 energy levels, 4 layers of electrons. Whereas for rubidium, we've got 5 levels or layers of electrons. So rubidium's nucleus is going to be more shielded from its valence electron. So because we have 5 layers of electrons, we have greater shielding, we're going to have larger radius. And that's because we have more layers of electrons as shielding increases. Now we want to look at carbon and nitrogen. So why is the radius of carbon larger than the radius of nitrogen? So both of these guys have 2 energy levels or 2 layers of electrons. So that can't explain the difference between them because it's the same for both. So carbon is going to have 6 protons, whereas nitrogen is going to have 7 protons. So that means that in nitrogen, those electrons are more attracted to its nucleus. So that means they move in closer and your radius is smaller. So as we get a greater nuclear charge, as the nucleus becomes more positive, that means that my radius is going to be smaller because it pulls those electrons in closer to the nucleus. What column number corresponds to the following groups of elements? So halogens, sometimes they're called halides. That's column 17. Noble gases, these are your non-reactive, very stable gases because they already have a full octet of electrons. The alkaline earth metals are in column 2, and alkali metals are in column 1. For each of these, we want to draw the Lewis dot structure. So the Lewis dot structure is a diagram that shows us how many valence electrons are present in an atom, and it can also be used to show us how the electrons are bonding in a compound. So everything in column 1 is going to have 1 valence electron because all of these elements are going to be S1. They might be 2S1 or 3S1 or 4S1, but they're all S1, meaning that they have 1 valence electron. Second column has 2. Column 13 would be 3, and then 4, 5, 6, 7, and 8. These ones in the middle, we'll deal with those later. Okay, so neon is going to have 8 dots in its Lewis dot structure. So remember, top, right, bottom, left, top, right, bottom, left. Since neon has no unpaired electrons, that means it's not going to form any bonds with other atoms. Sulfur is going to have 6. So for sulfur, 1, 2, 3, 4, 5, 6. Since sulfur has 2 unpaired electrons, that means that it can make up to 2 bonds. Okay, what about fluorine? So fluorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Since fluorine has 1 unpaired electrons, that means that it can make 1 bond, up to 1 bond total. Hydrogen has 1 valence electron. And remember that for hydrogen, stability is just 2 electrons. So since hydrogen here has this 1 unpaired electrons, that means that it can also make 1 bond. So F and H are the ones that are able to only form single bonds. For question 7, we have the Bohr model here, and we want to show the correct number of protons, neutrons, and electrons for a neutral atom of oxygen 16. So oxygen is always going to have 8 protons. The 16 here is the sum of the protons and the neutrons. And since we have 8 protons, we must also have 8 neutrons. And because this is a neutral atom, the number of electrons is equal to the number of protons. So in my nucleus, we have our 8 protons and our 8 neutrons. If we write out the electron configuration for oxygen, the first energy level is going to have 2 electrons in it. And then the second energy level has a total of 6. 1, 2, 3, 4, 5, 6. This is why oxygen can make up to 2 bonds, because it has 2 unpaired electrons. So for each of the following, we want to determine the chemical formula of the ionic compound. So the total of charges should always be 0 in an ionic compound. It should be overall neutral. So sodium is going to form a +1 charge because it has 1 valence electron and it's going to lose that 1 electron. So for sodium, we would put Na+. Oxygen forms -2 in its compounds because it needs to gain 2 electrons here. So we want to make sure that these charges add up to 0. So right now I have +1 and -2. That adds up to -1. So if I bring this 2 down here and I bring this 1 down here, I get this formula here, Na2O. So each of these sodiums is +1. We've got 2 of them. And then oxygen is -2. So when you combine those numbers together, you get 0, and that's how you know that this is the correct formula for this compound. Next, we have calcium +2 and hydroxide. So we can do our little crisscross of the charges. So I'm going to bring this 2 down here, and I'm going to bring this 1 down here. So that gives us this formula here. Now notice that I put the OH in parentheses, and that's because if I wrote something like this, we would think that it was CaOH2 as opposed to calcium and 2 hydroxides. So we want to make sure anytime we have one of these polyatomic ions that we are including a parenthesis around it. So there is 1 calcium that gives me +2, and each hydroxide is -1. So once again, this adds up to a total charge of 0. Aluminum and sulfate. So aluminum is going to form a +3 charge, and that's because it's going to get rid of 3 electrons. And then we have sulfate. So sulfate is a polyatomic ion here. So polyatomic means many atoms with one charge. So sulfate is SO4. So this is a single sulfate ion. And the charge on this sulfate is 2-. So I'm going to go ahead and put this guy in a parenthesis. I'm going to bring the 3 to here, and I'm going to bring the 2 to here. So Al2, SO4, 3. So again, we need a parenthesis around SO4 because I'm trying to say that there's 3 sulfates, not SO43. So each aluminum is +3, and there's 2 of them. Each sulfate is -2, and there's 3 of them. So that adds up to +6 and -6, giving us an overall charge of 0. For Mg +2 and N -3, so I can crisscross these charges, and I get Mg3N2. So there are 3 magnesiums, each of them is +2, and there are 2 nitrogens, they are each -3. So then when we add up these charges here, we get a total of 0. A student performed a lab to determine the identity of the bond type of several samples. Their data is found below. Identify each compound as ionic, metallic, polar covalent, or nonpolar covalent. So let's start with metals here. So metals are going to have a really high melting point, and they're not going to dissolve in polar or nonpolar solvents. So sample D here must be a metallic bond. If we look at sample B, we see that sample B has a very high polarity and the highest melting point. It dissolves in water, which is a polar solvent, but it won't dissolve in oil. So based on that, we would conclude that this is an ionic bond. C and D are both the same, so they're not polar, and they have low polarity. They dissolve in water, which is a polar solvent, but they don't dissolve in oil, and they have low melting points. So these are both going to be polar covalent. If it were non-polar covalent, we would see that it dissolves in oil instead of water. So we want to look at an atom of sulfur 33. So let's start with our electron configuration here. So sulfur is going to have 16 protons. Sulfur 33 means that there are 17 neutrons. And because this is neutral, we're also going to have 16 electrons. So I'm going to keep going until I've used 16 electrons here. So 3s2 and then 3p4. So we want to draw a Bohr model including protons, neutrons, and electrons in each energy level. So my nucleus is going to be 16 protons and 17 neutrons. And then in my first energy level, I'm going to have 2 electrons. My second energy level is going to have 8. And then my last energy level, my third energy level, is going to have a total of 6. So how many valence electrons? Remember that valence just means the highest energy level. So that's going to be a total of 6 valence electrons. In the next question, we want to identify the unknown element in the spectrum below. So what we're doing here is we're really just trying to match the atomic emission spectra of the unknown to one of our known elements here. So if we look at strontium, we see that this matches exactly all of the lines that are in the unknown. So that tells us that my unknown here must be strontium. Okay, so we have this table here, and we're looking at a couple of elements. So my first element that I have here is phosphorus. And this is going to be phosphorus 31. Its mass number is 31. Its atomic number is 15. The atomic number is the same thing as the number of protons. And since my charge is 0, I know that I have the same number of protons and electrons here. Now my mass number is 31, and 15 of that is protons. So the other 16 must be my neutrons. So now we have chlorine 36. So 36 is my mass number. I can use my periodic table and look up chlorine, and I see that its atomic number 17, meaning that it has 17 protons. My charge here is -1, so that tells me that I must have one more electron than proton. My mass number is 36, and 17 of those are protons, so that must mean that the other 19 are going to be my neutrons. So to make my symbol, I put the atomic letters, the atomic symbol here, and then this is going to be 17 for my atomic number, 36 for my mass number, and -1 for my charge. So now we want to describe how to find the average atomic mass given the abundances and masses of several isotopes. So you're going to take your percent abundance and convert that into a decimal just by dividing by 100. And then you're going to multiply that by the mass of the corresponding isotope. And so you're going to solve that, and you're going to get some number here. So you're going to repeat this for each isotope and get your answer here. And then you want to add together all numbers that you get after you do the multiplication. So if you had 5 isotopes, you would do this calculation 5 times, 1 for each isotope, get your answer, and then add all of those together. So the model below shows a hydrogen atom. An electron relaxes from the second energy level to the first energy level, releasing a photon of light with a wavelength of 656 nanometers. So how do electrons move between energy levels? So when they absorb energy, that is going to cause them to jump up to a higher energy level that we call the excited state. This excited state is not very stable, so that electron is going to re-emit that energy that it just absorbed, and it's going to jump back down to its ground state. So the difference in energy between the excited state and the ground state, that is equivalent to the amount of energy that is being released by that electron. And that energy is going to have a frequency and a wavelength associated with it. So that's why we see these different colors of light. Now we want to convert our 656 nanometers into meters. So nanometer needs to be on bottom to cancel and meter on top. Nano means 9. So 1 meter is going to be 1 times 10 to the 9 nanometers. So when I solve this, I get 6.56 times 10 to the -7 meters. This is important because if we want to use this in any calculations, our standard units are meters, not nanometers. So now we want to calculate the frequency of this photon. So we're going to use this equation, and I'm just going to rearrange this to solve for frequency. So that's going to be velocity over wavelength. We're talking about light here. So my velocity is going to be the speed of light, 3 times 10 to the 8 meters per second. My wavelength is going to be what we just solved for. We converted this from nanometers to meters. So 6.56 times 10 to the negative 4 meters. So meters will cancel, and we're just left with 1 over second, which is per second. That's frequency. So we get 4.57 times 10 to the 14 per second. You can write s minus 1, or you could write 1 over s. They both mean the same thing. So now we want to calculate how much energy was released. So energy is equal to Planck's constant times frequency. So Planck's constant is going to be 6.626 times 10 to the negative 34 joule seconds. And the frequency is what we just solved for in the previous question. So seconds will cancel seconds, and the only unit left will be joules. So we get 3.03 times 10 to the negative 19 joules.